Hello everybody, and please welcome to the presentation of the work I have done on facial expression recognition of neurologically impaired children. I'm gonna start with a short introduction, then I'm gonna talk to you about NeuroChild, the project for which this work has been done. Then we're gonna make some general considerations about building automatic facial expression systems. I'm gonna describe to you two different methods we have developed and the experiments and results obtained, and we're going to draw some conclusions. So, let's begin with the beginning. Facial expressions and facial expression analysis. Facial expressions are vital communication channels between humans in social contexts. When we are talking to somebody and we are looking to his or her face, we can tell gender, race, or, for example, how this person feels or thinks. This is why, across centuries, many artists have used facial expressions in order to produce strong emotional responses into their viewers. If we would be able to teach computers to detect and analyze facial expressions as humans do naturally, then we would be able to build better human-computer interaction applications. We could use it in, for example, gaming to improve the way we interact with virtual characters, or we could, of course, grow a better understanding into human emotion in general. There are many challenges to this. For example, we have to deal with head pose variations. We have to deal with various illumination contexts or with occlusions. But there are already many applications, either in research or on the market. Let me tell you a few words about the NeuroChild project. The NeuroChild project is a joint project financed by the Ministry of Economy and Competitivity in Spain. Several institutions will work together in order to develop a framework for patient progress assessment during rehabilitation sessions. Among these institutions, the Computer Vision Center, the organization we are working with, or we are working for, is going to do research and development for the facial expression recognition framework. Other institutions are going to work on defining affective states, on integrating results of this work into web applications, or on eye tracking methods. In the end, NeuroChild will consist in various modalities, a combination of modalities, that is facial expression, eye tracking, or head pose, to recognize complex affective states. And, as I said before, some of these results are going to be integrated into web-based products. First, we have developed a capturing data scenario. Children, aged between mostly 5 and 14 years old, are playing specially designed games which have in mind contexts which build strong emotional responses. While playing these games, we mount a camera and an eye tracker on the monitor they are looking to in order to capture their reactions to the game. By analyzing this context, we want to see how these emotional responses develop through time. Now, we have developed a short list of affective states we would like to detect. Here, as you can see, we are talking about emotional states like being happy or amused, being surprised, or being angry, or cognitive states like are the patient interested, or are they getting bored? Or we could detect things which are more larger term, like for example, are the patients impulsive or nervous while they are playing the games? What would you need for building an automatic facial expression analysis system in general? Well, first, you want to describe what you see on the face. This is why, in the 70s, mostly in the 70s, researchers from psychology have developed what is called a facial action coding system. This is largely used by all methods in facial expression analysis. Also in the 70s, research has reached the conclusion that there exists a subset of emotion which correlate with a specific facial expression which are universal and they do not depend on culture or context. These expressions are called the universal facial expression of emotion, and they are discussed: fear, happiness, surprise, sadness, and anger. What would you need for automatically analyzing facial expressions? First, you need to localize the face. Then, you need to detect the structure of the face, the eyes, the mouth, the nose. Based on the structure, we are going to build a representation of the face. And then we're going to use this representation to train classifiers in order to distinguish between predefined classes. In our case, facial expressions. Well, in order to detect facial expressions, we have developed two methods. But first, I'm going to talk to you a little about some things that are going on in the representation and recognition phase, the last two steps of a facial expression analysis framework. We have to say that there are two ways of representing a face. The first way is what is called a pre-designed representation. A pre-designed representation means using general descriptors that could be used for many other different problems. These descriptors can be geometry descriptors, appearance descriptors, or mixed descriptors, and they can be captured on a single frame or on multiple frames, dynamically, statically. On the other hand, there exists a second approach of learning the best representation that optimizes our classification. Also, in the last step, in the recognition step, we can talk about continuous recognition among different classes and categorical recognition among different classes. Between the pre-designed and learned representations, there are several differences. First, if you are using a pre-designed representation, of course, choosing the representation is an empirical thing. You don't exactly know what is your best representation. You're going to try several, and by experience, you're going to tell, well, this is better than the other. And you have to tune parameters, and this can be cumbersome. But the main advantage is that smaller amounts of data are needed for training your classifiers. If you are learning your representation, then you are hoping to obtain the best representation problem for the best representation possible for your problem. But in order to do so, you need longer training times and, most importantly, larger amounts of labeled data. The main focus of our work was to compare between a pre-designed and a learned representation. In order to do so, we have developed two methods. The first method is using a pre-designed representation of appearance and geometry, which is captured in a dynamic way. That means from many frames, not just one. How does this work? Well, after the registration, we are getting 68 points on the face. for the structure, 68 landmark points, as they are called. From the 68 points, we are grouping them. We are grouping the 68 points into pairs and triplets randomly. And then we are looking first at the current frame. From the pairs of points, we are computing distances. From the triplets of points, we are computing angles. The distances and the angles are a geometrical representation of the face. From the same triplets of points, we are looking at the center of the triangle which these points represent, and we are computing a histogram of gradients, which is an appearance representation of the face. This is done for the current frame. Then we are looking at frames in the past. 6 frames in the past, 9 frames in the past, and 12 frames in the past, in our case. For all these frames in the past, we are building from the same pairs as in the first step for the current frame. We are computing distances. And we are looking to see how these distances changed from 6 frames ago to the current frame, or from the 9 frames ago, or from 12 frames ago. This is for getting a representation of how our facial expression is evolving through time. After having this 4 representation of the current frame and of 3 transitions, we are reducing the dimensionality of the feature vectors through a classic PCA approach, and then we are feeding the reduced vectors to a random forest in order to distinguish between the 6 universal facial expressions I have presented to you before. The second method is a representation in order to perform exactly the same recognition problem. Okay? In order to do this, we are using a convolutional neural network with a topology, as you can see here. The faces are cropped and resized, and then are fed to a series of convolutional hidden layers in order to build more and more refined representations of the face. Once we are having the representation, then we are going to a fully connected part where these representations are classified into the 6 classes corresponding, each one of them, to a facial expression, a universal facial expression, as was the case before in the first method. So, let me talk to you about some of the experiments and the results obtained with these 2 methods. First of all, I would like to tell you that we have used, for training these methods, what is called the Extended Concanada dataset. This dataset is very, very well known, and it has been published in 2001. We have chosen this dataset first because it resembles a lot the conditions we will have in the NeuroChild project. We are dealing mostly with frontal poses, the illumination is controlled, and we have variations, or we have various ages. Also, using this dataset allow us to compare with many other methods, because this dataset, has been used extensively in the past 10-15 years. So, for the first method, we wanted to see if our pre-designed representation is discriminative enough for our facial expression analysis problem. In order to do so, we are plotting expressions of highest intensity along the first 2 principal components of a principal component analysis. Now, what you can see is that along the first principal component, we are coding the largest variations of the face. Both mouth and eyebrows are going from closed to largely opened. The second principal component is coding the variation of the anatomical component of the face, which has the largest deformation. In our case, this is the mouth. So we can conclude that this representation is distinguishing, discriminative for our facial expression analysis problem. Well, what we wanted to see is how many trees we would like to use for our random forests. In this plot, you have accuracy depending on the number of trees, both in the static and in dynamic case. The conclusion is that 50 is the optimum number of trees for the random forest. Then, we wanted to see how many tuples, pairs, or triplets of points from our registration should we use to build our representation. If we are using a small amount, for example 30, then accuracy starts decreasing because we are losing details of the face. If we are using too many, for example 300, then we are starting adding noise and accuracy decreases as well. If we are using 100, then we get an optimal representation of the face for our problem. The next thing we wanted to see is how many transitions should we choose and at what points in the past. Here, by order, we mean how many transitions are we adding to the current frame. If we have an order 0, then we are talking about a static representation. We are looking just at the current frame. If we have an order 1, then we have the static representation and 1 transition in the past. 2, static representation and 2 transitions in the past, and so on. Now, as you can see, an order 3 is optimal for our problem. But I have to say that this can be misleading. Why? This doesn't mean that if we would go further away in the past and with maybe more transitions, we couldn't achieve even higher accuracy. The problem is that the extended Concanade dataset doesn't have very long sequences, so we are limited on how far we could go in the past. This is why it is better said that an order 3 is optimal for this dataset we are using. With other datasets, we could probably go to even higher orders. Here, I'm presenting you how the first method is performing for distinguishing between each of the facial expressions we are targeting. As you can see, facial expressions of fear or of happiness, or of surprise actually, not happiness, surprise, are very well recognized. Why? Because fear or surprise are very distinctive among the 6 facial expressions. They are different. It's easy to recognize them. But if you look to anger and sadness, for example, this becomes a more difficult problem. It's not that easy to tell between anger and sadness if you are looking just at the current frame. If you are adding transitions and you are looking at how the facial expression is evolving, then it gets easier to distinguish between the 6 facial expressions. So, a dynamic representation performs better even for each of the facial expressions, not only on average. Now, let's make some comments about the second method. Remember, the second method is the method that tries to learn the optimal representation for our classification problem. In order to do so, we have expanded data we have regularized data in order to fight overfitting, and we have used different adaptive learning rates. Still, we couldn't get above 78% accuracy. The problem is that it is difficult to obtain higher performance with the amount of data we have. In order to obtain higher performances, we would need larger amounts of data. And this is the main conclusion of the second method. Here, you have the final configurations of the two methods with the main parameters and some of the programming languages we have used and the editing techniques. And here you have a comparison of performances between our two methods and similar methods which have been published in the literature. As you can see, the first method achieves not very good results, but the first method is obtaining very good results which are comparable with state-of-the-art methods in similar conditions. Now, as we are starting to capture data from NeuroChild, we can already draw some preliminary conclusions about the actual data in the context we are targeting. What you can see here is a sequence of a patient where the first two steps of localizing the face and registering the face have been performed. Now, some conclusions can be drawn. First, in the context of NeuroChild, we will have to deal with rotation of the head. And second, as you can see, the patient is bringing the hand, frequently bringing the hand to the face, which means that this is going to occlude the face and this is going to cause registration problems. So let's draw some conclusions. Well, we have developed an extended state-of-the-art for determining the most appropriate methods for solving our problem in the NeuroChild project. Then we have designed a framework for automatically assessing patient progress and a capturing data scenario. Two approaches have been already tested. The first approach performs very well with state-of-the-art results by taking into account the dynamic of the facial expression. The second method, which is based on learning the representation, needs more amounts of data in order to achieve state-of-the-art performance. Future work will mean that specially trained persons will start labeling the data captured from your NeuroChild project, and we're going to start training the methods proposed with the labeled data. When doing so, we'll have to take into account challenges like head pose variation and occlusions. Also, important to mention is that for recognizing cognitive states or mood, we will probably have to combine facial expressions with eye tracking and head pose. Thank you.